I've chosen to start on this slide in Lecture 3 because it's one of my favourites, or more realistically because this is where really I start to change tack. So this is just to introduce you to the concept of System International or SI units, those of you who aren't used to science. Most of you obviously will be familiar with the basic ones like kilograms and grams and kilometres and metres. And I've just used the abbreviations here, the M and the G and the tera and everything. And you can also go the other way, of course. You can go to milli as you go down picograms and femtograms and things like this. But we don't have a lot of use for that in this unit. So really, I'd like you just to focus on the use of, say, the capital M and the K for thousand. Now, saying goodbye to our magpie, and we're going to move on to the mean density of the Earth, as I've said in the last slide, is just over 5.5 grams per cubic centimetre of Earth. Now, that mean density is if you were to take the whole planet and blend it so that it was homogeneous. We know it's not homogeneous, and so consequently this 5.5 grams is the impression that you would get if you were assessing the density of the whole planet from some distance away in space. I have mentioned the fact that the magnetic field does reverse polarity from time to time, and I've just given you a little bit more data here. Over the past 10 or so million years, then we know that there has been about 4 or 5 reversals per million years. That's the MA, million annum, mega annum, -1 is the per symbol, of course, so per million years. And so that means over the last 10 million years, there's been about 40 or 50 changes in polarity. And so you can see that they do happen about every 200,000 years if there's 4 or 5 per million years. So they're not actually that fixed, the magnetic poles. And as I've said in an earlier lecture, we do know that the intensity of the magnetic field varies enormously as well. And at the moment, the magnetic field is definitely weaker than it was, weaker than it has been degrading in strength over the past few hundred years, and is certainly not as strong as it was a few thousand years ago. That is often proposed to be the, advertising the fact that we're about to switch poles, because we do know that just before the North Pole goes from the North Geographic Pole to the South Geographic Pole, we do know that the gravity does become considerably weaker as this process occurs. However, I wouldn't like to predict it. It could happen within a couple of years, or it could happen within a couple of tens of thousands of years, but there certainly is one due, because we have been in this chron for almost 200,000 years or so now. So we are due a change. Now, the shallow geothermal gradient, the geotherm, is how we refer to the change in temperature with depth within the planet, within Earth. Geo is Earth. And the gradient is just, as I say, the rate of change. So in the top 3 to 5 kilometres of crust, then you're looking at this is actually continental crust, then you're looking at a change in gradient of about 30 degrees centigrade for each kilometre you go down. So hence, when you go into deep mines, the temperature becomes unbearable and people find it very hard to work. As I say, this is continental crust. If this was oceanic crust near a mid-ocean ridge, the geothermal gradient would be considerably higher than that, because you would have to get down to a temperature of about 1200 degrees C within that 5 kilometres. So you can imagine the geothermal gradient would be huge. The geotherm does vary depending on where you are and how thick the crust is, whether or not there's been any magma in accumulation in the crust, whether you're near any volcanism, how much fluid there is circulating through the crust, what concentration of radioactive elements there are, etc., etc. So there's lots of variables, and even on continental crust you can have very different geotherms, but on average it's about 30 degrees centigrade per kilometre. Okay, now this solid bit is the difference in viscosity. We talk about the lithosphere being solid, but we mean it's solid relative to the asthenospheric mantle underneath it. And I was asked a very interesting question about viscosity. Think of everything as having as being viscous. Okay, and the scale for viscosity is huge. So, for instance, window glass is viscous. It has a viscosity. Window glass will flow with time, and it is common in windows that have had glass in them for a couple of 100 years or more for the glass at the bottom of the window to be much thicker than the glass at the top, because it has flowed with, because of gravity. In a warmer country like Australia, I would expect that to happen quicker, because I would have thought it would have speeded the reaction up. Certainly in England, when you're looking at houses from the 15, 16, 1700s, then it is quite noticeable just by looking through the glass that you have thicker distorting glass at the bottom and thinner at the top. Also, ice flows. Think of solids that flow and solids that you can have a viscosity to, but you're just looking at a different flow rate. Think of the mantle as behaving not dissimilar to ice sheets, for instance. I know this may not be the world's best analogy for an Australian, but you have seen ice sheets on documentary programs and things. So really, when we say the lithosphere is behaving as a solid, or it's behaving in a more brittle manner, it is, but that is relative to the rest of the planet. Okay, so I don't want you running away with the idea that the lithosphere is, completely brittle. It's not. We can get folding happening in the crust where, obviously it hasn't broken, it's folded, it's undergone a ductile or a plastic behaviour. But relative to the mantle underneath, it is behaving like a solid. And as I say, without this difference in viscosity and behaviour, then we wouldn't have plate tectonics as we know it. Now, minerals usually, as I've said, don't go out on their own. They usually do combine with each other to form rocks. Rocks are nearly always polymineralic. They have many different types of minerals in, or some different types of minerals in. Very, very few rocks are monomineralic. And the best example of a monomineralic rock, or almost monomineralic, would be a sandstone. And a sandstone, a siliciclastic sandstone. And this is a rock that is formed of bits of clasts, which are actually in this case mineral clasts. They're broken bits from other rocks, and they are all made of quartz, and they are well rounded usually. So the siliciclastic means broken bits of quartz, and it's a sedimentary rock that you can see forming on the beaches today in many parts of Western Australia. It would be a very pure white sand that you would be looking at. Obviously, though, on the sand you get broken bits of shells, and in that case you would end up with a sandstone which is composed of quartz grains and grains of shell, or broken bits of shell clasts, which would be bioclasts. It's all quite logical, and I don't need you to go this far. So minerals usually combine to form rocks. Minerals are defined as being naturally occurring, so you can't include anthropogenic minerals. You can't include things that we create, like in synthetic diamonds and synthetic corundum and things like that. It's inorganic, so there is no, you can't look at any of the biomineralization, because the word bio immediately means that we don't treat them as minerals. So you don't look at the way that the material that shells are made of is not minerals, your bones, teeth, etc. Pearls are not minerals. And also it's a chemical compound. Now, also minerals have to be solid phases at surface temperatures and pressures, i.e. they have to be solid, not liquids, at surface temperatures and pressures. And importantly, they must be crystalline. They must have an ordered three-dimensional structure, an atomic structure, where the elements, or present as ions in that lattice, are arranged in a repeating way. It must be a systematically repeating structure. And it is indeed this structure that makes a mineral crystalline, and the structure and the chemical composition of the mineral that defines the mineral. And so a pearl falls down on two grounds. It's biological, and it also doesn't have a crystalline structure. Okay, so a mineral is defined by its chemical composition and its structure. I'm going to leave it there and start another one for the next slide, which will be the composition and groups of minerals, because these are easier in bite-sized slices.